Hi everyone, welcome back to yet another Euphoria Academia YouTube video. Today we're going to be doing Physical Science Paper 1 that was written in November 2024 and it is for the National Senior Certificate. We're going to be doing the questions that are relating to Newton as well as some questions that are doing or have to do with kinematics. My name is Ole and I'll be taking you through it. So without further waste of time, let us get into it. Okay, we're going to be starting off with some multiple choice questions, just to get a bit warmed up for the main questions. So we just have to circle the correct answer, right? So for question 1.1, we are told that several forces are acting on a moving object. Which one of the following statements is correct when these forces are in equilibrium? So when forces are in equilibrium, we know that the sum of the forces should be equal to 0, right? And this 0 essentially means that the acceleration is 0, right? That's essentially what it means. So two conditions exist when acceleration is 0. This is when we not moving, so velocity is 0, right? Therefore acceleration is 0. The other one is we can have an acceleration of 0, but the velocity can be constant, meaning we're moving at one speed. All right, so let us see which one of these conditions we're given. Right, so which one of the following statements is correct when these forces are in equilibrium? The velocity of the object is increasing. Well, that's the definition of acceleration. So no, sum of forces will not be equal to 0. And then the object is moving at constant velocity. Well, that is one that we have, but let's continue reading. This essentially this is what we want. That's true. And then number C says the kinetic energy of the object is decreasing. No. The object has a non-zero acceleration. No. So that means our most correct or only correct answer has to be B for 1.1. Alright, let us move on to a kinematic question now. A stone is thrown vertically downwards from the top of a building and it takes t seconds to strike the ground. Consider the acceleration time graph below for the motion of the stone. The effects of air friction are ignored. So this is a one-dimensional projectile motion essentially. And we're asked, what does the shaded area between 0 and t seconds shown in the graph represent? Alright, so we have a constant acceleration, and if you are to take the area, which you will learn later, that is the integral of this function, we're going to find that the integral of this function, or the shaded area, is actually equal to the change in the velocity. So let's see which one of those answers are here. The final velocity, no. The change in position of the stone, no. The constant velocity of the stone, this is where a lot of students get it wrong. It's not the constant velocity. If it was constant velocity, we wouldn't have acceleration. So in this case, our acceleration is not equal to 0. So we have an acceleration, a constant acceleration, mind you. So as we said, the area is actually the change in the velocity of the stone. So D is our answer. All right. Okay, question 1.4. We're told that a force F acts on a box as the box moves from rest down a rough incline. So there's motion of this box at a constant acceleration. The force is parallel to the incline as shown in the diagram. Alright, so we're told that the box moves from rest down a rough incline. So we can already assume that there is some sort of friction, and if there's movement, we have kinetic friction. And the force F, we don't really know what this force F is coming from, but we're told that there's a force F, and this arrow indicates that there is motion down this incline. All right, so we have to choose the option correctly that completes the following statement. The work done by the gravitational force is it equal to, less than, or greater than the sum of, or equal to the difference between the work done by the frictional force and the work done by the force. So if this thing is on an incline and we have a force pulling it this way, force F, pulling it that way, our frictional force, just because there's motion down that way, frictional force opposes the direction of movement, right? So we're going to have our Fk in that direction. So that means opposing this motion. In this case, the force that is propelling this down is our force of gravity. In this case, it'll probably just be mg cos whatever this angle theta is. All right, and we'll have a combination of our force F and our frictional force. Right, so we essentially need to look for a statement that says the sum of. All right, okay, so all of them, or not all of them. So already we can see that D is out. Okay, so we have to choose A, B, C, but because this thing is moving down the incline, because there is motion, that means it has to be more than both of these forces, right? So the answer that we have is actually C. Okay, now let us quickly do question 1.5. Question 1.5 says a ball is falling vertically downwards from point A. It's falling vertically downwards from point A, strikes the ground with the velocity v, and bounces, reaching a maximum height at point B in the diagram below. Which one of the combinations is correct? For the direction of the impulse on the ball striking upon. So already because they're asking us about the direction of the impulse, well, the impulse is actually pointing in the upward direction because there is a change of direction just like that. So that is a contribution of the impulse. So already we can scratch out number B and number D. So now we're just looking at A and C, and we need to, the next line is to discern the magnitude of the velocity with which the ball leaves the ground. So indicated on this diagram, it doesn't travel that far, right? So that might mean that this velocity is not nearly as much as that velocity over there. So it has to, the direction of the impulse is upward and it is less than v. That's our answer for these multiple choice questions. Right, now moving on to the main question that we want to attempt, which is question 2. It ranges from question 2.1 all the way to question 2.4, and it is a maximum of 15 marks. So let's get into it. Let's understand exactly what's happening here. All right. I like doing this analysis because moving forward, it's going to help us do the questions. Always give yourself time to understand what is happening in the question so that it's easier for you to answer as well as quicker for you to answer. All right, so question 2 states that in an experiment we have a crate of mass 8.5 kilograms, all right, lying stationary on a rough horizontal table. For the mere fact that they said rough, we know that we're going to have some sort of friction, and it is stationary. So if it's stationary, the friction that we have is the static friction. All right, and it is connected to a mass hanger by means of a light, inextensible string. This basically means that the string, sorry, does not have any mass, as well as it doesn't compress nor does it extend. So it essentially means that the crate and the mass hanger are connected, and the string isn't gonna add or subtract the forces. It's just a way of connecting these things. That's what it means. Over a frictionless pulley, that's exactly what it means. There's no friction in the pulley, so it doesn't add any resistance to the system. As shown in the diagram below, mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. Ignore the effects of air friction. They didn't say all frictions, just air friction. Alright, so the results obtained give us this graph. So what we can discern from this graph is that we have the hanging mass, so masses associated with that hanger over there on the x-axis, and the acceleration of the crate, and by virtue of the mass hanger on the y-axis, right? Because these things are connected by the string, right? So what does this graph tell us? Well, it tells us that from 0 to 4.2 kilograms of that mass hanger, there's no movement. And then after 4.2 kilograms, we don't know exactly at which point, but we start having acceleration. So it moves after 4.2 kilograms, but before the 4.2 kilograms, it's still static. So that would mean that the force of gravity on this thing, mg, will not be enough to pull this crate along if the mass is smaller than 4.2 kg. Alright, that's essentially what it means. So let us get into the question, since we actually understand what is going on in the system. Alright, so this is not 8.1, it's question 2.1. It asks us to essentially, it asks us to define what static friction is. Alright, and yeah, that is not working. It's question 2.1, apologies. It asks us to define what static friction is. So as always, please study your definitions, but essentially it's a force, just get in your keywords, those are important. A force that opposes, that is how you, yeah, opposes motion, right, or the tendency of motion of a stationary object. So I'm not gonna write everything, but yeah, just know that it opposes the tendency of motion. Of motion of a stationary object. I'm not gonna finish the stationary object that is parallel to surface. Alright, so the key things that you need to note is that it's a force or opposes motion, and then of a stationary object, and then this indicates the direction. How does it act? It acts parallel to the surface. Just note down those things. Question 2.2 is asking us to draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. So just before it starts moving, that means we have static friction, that's the crate. or a not so great representation of it. And before it starts moving, we still have the hanger connected to it, but it's connected via tension. And then what's opposing the motion? We're just looking at the horizontal questions. What's opposing the motion is static friction. And that's your 2 marks. All right, so let us move on. Question 2.3.1 is asking us to calculate the coefficient of static friction. So let's just write the question number. So we're meant to find the coefficient of static friction, right? Now, how are we going to do this thing? So essentially, to find the coefficient of static friction, we know that we have to use our maximum static friction, right? This is the point where there's just about to be motion. So there's no motion, but like maybe in a couple of milliseconds, we're going to have some motion, right? And for our experiment here, at which point was that? Well, we can see that on the graph that when the hanging mass is at 4.2 kilograms, slightly after it, there begins motion, but before it, there isn't motion. So we can say that that's the critical point. All right, so let us set up our system of equations, and yeah, let us begin with the question. All right, so we know that we have the crate. We're just gonna divide it up now. All right, so for the crate, what forces do we have? Well, already did it in the question before it. We actually have tension acting to the right, and then the friction acting to the left, which is where we're going to get this guy. All right, cool. So let us write that equation. So we know that our sum of forces will actually be equal to 0 because we don't have motion, right? And we can take that our right is positive. All right, so if right is positive, we have tension minus the maximum frictional force, right? And that will be equal to 0 because of the reason stated. There's no acceleration, there's no movement, and we don't know what our tension is equal to, but we can substitute in our equation for maximum static friction, which is mu s multiplied to the normal force. Now the normal force is just the mass multiplied by the force of gravity, and that is equal to 0. We can continue doing our substitutions. We're still trying to find mu s, and our mass is 8.5 kilograms, and our force of gravity is 9.8, and that is equal to 0. And we will find that our tension is equal to our mu s multiplied to 8.5, which I think it's fine. I'll just leave it as that. We'll just do the substitutions later. All right, now we have that for the crate. Now for the hanging mass, what do we have? Because we're still trying to find our tension. You find our tension, we'll find our mu s. For our hanging mass, we have that still the sum of our forces is equal to 0, and we'll take down as positive because the tension in this case is going to stop or prohibit this thing to move. All right, so we always like to favor the force that is pushing this thing to move in a specific direction. all right, and that will be our force of gravity. So that will be our mg, right? In this case, it will be the hanging mass multiplied by the force of gravity minus the tension. That is going to be equal to 0. And what is our hanging mass at? Well, we already said that it's at our 4.2 kilograms, and we're just going to multiply that by 9.8, and that minus our tension is going to give us 0. And when we do some mathematics, we will find that our tension is equal to 41.202, and we're just going to substitute the value of our tension. Actually, no, I wrote the decimals wrong. That's not, still 41, apologies, but that's 41.16 rather. Alright, so we're just going to substitute that into that, and we're going to find that all of that is equal to our mu s multiplied to 8.5 multiplied to 9.8, and when you divide 41.16 by this product, we're going to find that our mu s is equal to 0.49, and that is our answer. That's our coefficient of static friction. Alright, so now we're doing question, oops, wrong color. We're doing question 2.3.2, and question 2.3.2 is asking us to find our y, so this acceleration here. And where do we find this y? This is when our hanging mass is going to be at a value of 7.4 kilograms. So we already have motion, so our F net is not equal to 0. So that's one thing that we do know. We know that it's equal to our y. Now, since our hanging mass and our crate are connected by this extendable as well as the frictionless pulley, we know that whatever translation of acceleration for our hanging mass is going to be equal to the acceleration of our crate. By that, we just need to set up our equations and just see what we have to equate, and the tension is still the same. All right, so we're going to first start off with the crate. All right, so for the crate, we're going to have a situation where we still have our equation of still using Newton's second law. F net is equal to ma, where our sum of forces is going to be positive to the right, and we're going to have a situation where we have our tension minus, we have motion now, so our kinetic friction, sorry, is going to be equal to our mass times our acceleration, and we're told that the coefficient of kinetic friction is 0.4. Alright, so let's just do our substitutions. Now we can't use this tension from the previous question because we have motion now, so that means this force is going to be different. We're going to be pulled by the mass hanger differently in terms of magnitude. Right, so let's just substitute what we have for Fk, which is our coefficient of kinetic friction. That is going to be multiplied to our mg, and our mass in this case is still 8.5. This is for the crate, and that is going to be multiplied by our acceleration y. Let us do some further substitutions. Our mu k is going to be equal to 0.4. Our mass is still 8.5. Gravity still 9.8, and that is equal to 8.5 y. Now let us do some simplifications. Let's just move everything to the right hand side that we can compute. We're going to leave t on the left hand side alone. So our t is going to be equal to 8.5 y plus, now what is the product of all those things? That's going to give us 33.32. All right, we can call that our equation 1. All right, now for the hanging mass, so I'm just gonna write hanging mass. I was gonna write hangman, but it's not that type of show. So we still have our sum of forces, right? Our F net, that is still equal to ma. We have movement, our acceleration is not 0, and we're going to take downward still as positive. So what are our forces? So we have the force of gravity, so I'm just going to write mg minus the force of tension, that is going to be equal to our ma. So let us just do some substitutions. Our mass in this case is 7.4, that is multiplied to 9.8, that is still subtracting our t, that is still 7.4, and our acceleration is y. Alright, now what we're going to do is we're going to do some simplifications as well as mathematics, and we're going to find that our t, I also still want to write it in, or let me just say our minus t is going to be equal to 7.4y minus 7.4 times 9.8, that is going to give us 72.52, and let us just make sure that we have t in the positive sense. That is going to give us t is equal to 72.52 minus 7.4 y, and that is going to be equation 2. Alright, let me just write this. So we're trying to find our y, so let's write equation, let's substitute our equation 2 into 1, and we're going to find that we have 72.52 minus 7.4y being equal to 8.5y plus 33.32. And doing some simplifications, we're going to find that I'm just going to put the y expressions on one side and then the numbers on the other side. So we're going to say 72.52 minus our 33.32. We're going to find that we have 39.2 on the left hand side being equal to, now what is 8.5 plus 7.4? That is going to give us 15.9y, and our y will be equal to, we're just going to divide both of the sides by 15.92, and 39.92 divided by 15.9 is going to give us y is equal to 2.47 meters per second squared. That is our acceleration, and that is our question. Right, now the last question is question 2.4, and it asks us a 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the crate? So the crate that we do have had 8.5 kgs, and now 5 kgs is going to be placed on top. how is that going to affect the static frictional force? Well, essentially they're just asking us how do we calculate our Fs max, right? And that will be equal to mu S multiplied to our normal force, and our mu S, our normal force, is just the mass. So now we have 8.5 and the 5 kilograms, so that's going to be 13.5 multiplied to 9.8, and without doing much, if the coefficient of static friction stays the same, you can see that this will yield a higher number. So essentially the maximum frictional force will increase, so this will go up. So that's our answer, increases.